Hello everyone. In this session we are going to discuss about spanning trees. So this requires some basic understanding of graph theory. So what is a graph and how do we represent a graph, and the basic definition of a tree. We assume that people are familiar with the concept of graphs and trees. We will go ahead with the spanning tree session. So the objective of this session is to understand what is a spanning tree for a given graph and what are its general properties, its mathematical properties, followed by some of the applications that we have in our day-to-day life and in computer science in general, followed by a basic definition of minimum spanning tree. And the references used for this session are given below. Students are advised to go through these references for more details. Though most of the information will be covered during the presentation, you can browse through these particular things for more information. So let's begin with the general definition of a spanning tree. A spanning tree is defined for a graph. So in general, a spanning tree is defined for a graph. A graph is represented by a set of vertices and a set of edges. So a spanning tree for a given graph G, which has some vertices and some edges, is a subset of G such that all the vertices are connected with minimum possible number of edges. So that means a spanning tree is a subset of the graph. When we say is subset of the graph, so all the vertices are taken. Not all the edges are taken, but a few of the edges are taken such that all the vertices are connected to one another. So we need to ensure that we have a connectivity across all the vertices with minimum possible number of edges. So what does it mean? So it generates a tree. So assuming that we already know that a tree provides connectivity between every pair of vertices, and there is only one path between every pair of vertices. So obviously removing an edge from a tree makes it disconnected. So the same thing applies even to spanning tree. So if you remove an edge from the spanning tree, all the vertices become disconnected. So the connectivity will be lost. So, and adding an edge to the minimum spanning tree will create cycles. So we will have multiple paths between vertices. So anyways, an example would make this clear. So let's check an example. So here is a spanning tree. Here is a graph G which has 5 vertices A, B, C, D, E and a set of edges. As you can see, there is connectivity between AB, AC, AD and others. So there are 8 edges. So this is a general graph which is connected. So before this, we need to understand that we will have directed graphs, undirected graphs, connected graphs and disconnected graphs. So as far as spanning trees are concerned, we are going to look at only directed graphs which are connected. So we are not dealing with undirected graphs. So though we may have spanning trees for directed graphs also, we mostly deal with undirected graphs. So let's stick to that. We are going to use only undirected graphs. So as you can see, this particular undirected graph has 5 vertices and a set of edges. So from this we can derive certain spanning trees. So as you can see, the first spanning tree. So this is the first one. So this spanning tree has all the vertices, but we have selected only a few edges. So we have selected a subset of the edges. So all the vertices are selected, but the edges are selected such that there is only one and only one path exists between every pair of vertices. So we have, in this particular case, we have chosen AB, AC, CD and BE. So we selected only these 4 edges out of 8. So this is a spanning tree. Why is it a spanning tree? We have connectivity between every pair of edges, and removing an edge, for example, if we remove CD, we will have the vertices disconnected. So D will be disconnected. And adding an edge will make a cycle. For example, if we add DE, if we add the edge DE, there will be a cycle. So it does not support the property of a tree. Tree must not have any cycles, so we should not add any more edges. Otherwise the tree becomes invalid. That means it becomes a graph again. Likewise, let's take the second spanning tree. In this case also we have chosen a subset of the edges such that it forms a tree, and all the vertices are connected. So we have AB, we have BD, CD and BE. Adding any edge, adding one more edge will make a cycle, and removing an edge will make it disconnected. Likewise, we have the third spanning tree. So how many spanning trees can we derive? So at least intuitively we can say that we can have multiple spanning trees for a given graph. In this case we have 3, and in fact we can draw more. For this example we may be able to draw multiple spanning trees. So the point to be noted here is that we will have multiple spanning trees for a given graph. It is a very likely possibility. So let's take another example. So it's a small graph. It has 3 vertices ABC and 3 edges. It's a complete graph because each vertex is connected with every other vertex, so it's called a complete graph. For this complete graph we can draw 3 spanning trees. As you can see, if you remove AC, all these things are connected, so there is a path between every pair of vertices, though there is not a direct path between some of the vertices. For example, AB, BC are directly connected, whereas AC are connected through B. Similarly here AC are directly connected, B and C are directly connected, whereas AB is connected via C. Same is the thing with this particular spanning tree. So we can create 3 spanning trees here. We cannot create any more spanning trees. So for a complete graph with 3 vertices, we can have only 3 spanning trees. Let's look at another example with 4 vertices. So this is also a complete graph, as you can see. So we have 6 edges. So a complete graph with n vertices will have NC2, n into n minus 1 by 2 edges. So in this case we have 4 vertices, so we have 6 edges. So from this particular graph we can generate 16 spanning trees. So as you can see, this is spanning tree 1, spanning tree 2, spanning tree 3. So we can generate multiple spanning trees. So all these spanning trees are listed. So for a complete graph with 4 vertices, we will have 16 spanning trees. So the general question here is that how many spanning trees can we generate for a tree with n vertices? For example, how many spanning trees can we generate for a graph with 5 vertices? How many can we generate for a graph with 6 vertices? So this is a general question. So we will look at that particular point in the next slides. When we look at the mathematical properties, we will understand how many spanning trees we can generate for any graph, for any complete graph. We are only talking about the complete graphs. For incomplete graphs, it's not quite easy to derive the number of spanning trees. How many spanning trees we can generate is not something easily determined. So let's look at some of the general properties. We've already looked at these properties while looking at some of these examples, but let's list down. So as you can see, a connected graph, since we are talking about only the undirected graphs, an undirected connected graph will have more than one spanning tree generally, unless it is a very sparsely populated spanning tree. That means if you have only 2 vertices, then you will obviously have only one spanning tree. If you remove that edge, that both the vertices become disconnected. So in all other cases, so if a graph has more than 2 vertices, then the number of spanning trees is definitely more than 1. All the spanning trees have the same number of edges. This is an important point to be noted. So take any spanning tree of a given graph. So all the spanning trees will have the same number of edges. How many edges do we have? That we will look at in the mathematical properties. So the next thing is, since we are talking about trees, spanning tree is also a tree. So the basic property of a tree is that it should not contain any cycles. So similarly, spanning trees will not have any cycles. Intuitively, you can say that adding an edge to the spanning tree will create a cycle, because that is the least possible number of edges that make the entire set of vertices connected. So if you remove an edge, that becomes disconnected. If you add an edge, that creates a cycle. And only one path exists between each pair of vertices. Obviously, that is the basic property of a tree. So the same thing applies even to spanning trees. So these are the mathematical properties. A graph with n vertices will yield a spanning tree of n minus 1 edges. So this is a bit intuitive, but let's look at this with an example. So let's take this particular graph. A, B, C, D. So we have 4 vertices and some number of edges. In this case, we have 5 edges. So to make all these 4 vertices connected, how many edges do we need? Obviously, you need only 3 edges. So if you have n vertices, you need n minus 1 edges. So that is also a basic property of a tree. In order to have a tree with n vertices, you need to have only n minus 1 edges. So you cannot have more, you cannot have less. If you have less, the tree becomes disconnected. If you have more, it violates the very basic property of a tree and creates cycles. So obviously, the statement that a graph with n vertices will give a spanning tree, any spanning tree of a graph with n vertices will have n minus 1 edges. It's an intuitive statement. So the next thing is, how many edges do we need to remove? Because when you say a graph consists of cycles, unless the graph itself is a tree. So since we are talking about creating spanning trees, and we assume that the graph has cycles and we need to remove those cycles. So to create a spanning tree for a graph with v vertices and e edges, how many edges do we need to remove? Because we have additional edges, so we need to remove those all the additional edges to make it a tree. So if a graph has v vertices and e edges, we need to remove e minus n plus 1 edges to create a spanning tree out of it. So let's look at this with an example. So this is the graph. We have 4 vertices and 5 edges. So how many edges do we need to remove? Because as we've seen in the previous slide, we need to have only 3 edges. How many edges do we have? We have 5 edges. So we need to remove 3 edges. So 5 minus 4, which is number of edges minus number of vertices plus 1. So e minus n plus 1. So we will have to remove 2 edges. You can remove any 2 edges. It doesn't necessarily have to be, in this case we've removed AB and AD. It's not the case. You can remove BC and CD also. That also creates a spanning tree. So it only suggests that the number of edges that need to be removed we were only talking about the number of edges that we need to remove. It doesn't have to be the specific edges. So you can remove any 2 edges. So the next property, we've already looked at this. So the number of spanning trees that you can generate for a complete graph with n vertices. So this is what is necessary. So the statement says that a complete graph with n vertices will have n raised to the power of n minus 2 spanning trees. For example, if you have 3 vertices, you have 3. We've seen that in the previous example. So if you have 3 vertices, then you have 3 raised to the power of 3 minus 2. That is equal to 3. So similarly, if you have 4 raised to the power of 4 minus 2, 16. So if you have 5, obviously it is 5 raised to the power of 5 minus 2, which is equal to 125. So similarly, you can work it out for graphs with higher number of vertices. Obviously, if you have a high number of vertices, then the number of spanning trees generated will also be pretty high. Since we have only 4 vertices here, we could enumerate the entire set here. If you have more number of vertices, obviously it's difficult to enumerate all those graphs. perhaps you may have to do it programmatically. So these are some of the mathematical properties. Then let's have a quick look at some of the applications of spanning trees. Spanning trees are generally used in civil network planning. For example, you have a city, let's take a city or a town or somewhere where telephone lines have to be established. So we need to find out the minimum number of lines that need to be established to create connectivity across all homes. So how do you do it? So again, if you consider every home as a vertex and every line as an edge, so minimum number of edges that you need to create connectivity across all the vertices. So this is a classic example of spanning trees. Similarly, in computer networks we have routing. Packets have to be routed at different levels, at network layer, at transport layer. So there are several layers in the computer network. So across the layers we need connectivity, so between every pair of nodes. So how do you establish the connectivity? So what is the best way? The best way is to route the packets from one node to another node. So what is the best path to route the nodes from one computer to another computer? So we have different routing protocols there, and spanning tree protocol is a very popular protocol, so that there also we use spanning trees. Then we have clustering. So this is a very popular technique in data mining and machine learning. So where we find it's also known as the unsupervised learning. So to classify things we use spanning trees, though we don't have to go to details for this thing for cluster analysis. This is an example that clustering uses spanning tree approach. And pattern recognition, particularly to identify certain patterns such as handwritten text or certain objects with reasonable precision, with high accuracy, we use the spanning tree techniques there. So these are some of the useful applications where spanning trees are widely used. So you can probably go through some of the articles for more information on where spanning trees can be used. So now the next thing is to understand what is a minimum spanning tree. So a minimum spanning tree, we know a spanning tree is defined for a graph, but what is a minimum spanning tree? So when we talk about minimum spanning tree, we need to define a new attribute called weight, because so far we've discussed about only graphs without any weights for edges. That means every edge is treated as same. But in this case, certain edges may have higher weights than other edges. Maybe you can consider it like distance between two cities. So distance changes between every pair of cities. So likewise, or talking about the telephone lines, so the distance between every pair of homes. So you can consider the distance as a weight. So spanning trees are defined for weighted graph. So what does it mean? What is a minimum spanning tree? It is a spanning tree and it is defined for a weighted graph, and it has minimum cost. So any spanning tree that has the least cost for a weighted graph is defined as a minimum spanning tree. So what is cost? Cost is defined as the sum of weights of the edges of the weighted graph. So an example would make it easier to understand. Let's take this particular undirected graph. So you have 4 vertices and you have 5 edges, and each edge is labeled with its weight. So this is 1, this is 2, 3, 4, 5. So all the edges are weighted. Now how many spanning trees can we generate for this one? Obviously we can generate more than one spanning tree, but we want to generate a spanning tree such that its total cost is minimum. Total cost is the sum of the edges. So for example, this is a spanning tree. What is the weight of this spanning tree? 4 plus 5 plus 2. So this is 11, the cost of this particular spanning tree. Let's take another spanning tree. So this is 4 plus 1 plus 2, 7. So this is a better spanning tree than this one, and you cannot create any spanning tree whose cost is less than that of this particular spanning tree. So we can intuitively say that this is the minimum spanning tree for this particular weighted graph. So you can enumerate all the other spanning trees and calculate their weights, and you will find that the cost of those spanning trees is certainly more than 7. You cannot find any other spanning tree whose cost is less than this particular less than the cost of this particular spanning tree. So that is why we consider this one as the minimum spanning tree. So intuitively you may get a question, do we have more than one minimum spanning tree for a given weighted graph? Yes, that's a pretty much possibility, that's pretty much likely. But again, it is based on the condition that if you have edges with the same weights, if you have more than one edge with the same weight, then it is likely that we will have multiple spanning trees. But if all the weights are different, if the weights of all the edges are different, so then in that case we will have only one spanning tree. At least intuitively we can say that. So the next question is, how do we generate minimum spanning tree for a given weighted graph? That's the thing, because in this case you can enumerate all the spanning trees and then find the best one, but that's not a good solution. Obviously it's a tedious solution. So what is the best solution? The best solution is to have an algorithmic approach using which you can generate minimum spanning tree for a given graph, because it's in this case it is a very simple graph, so you can enumerate all these spanning trees and then find the best out of it, the one with the minimum cost. But what if we have some 20 vertices and some 100 edges? So it's very difficult to find to enumerate all the spanning trees and then find the minimum spanning tree out of it. So there are approaches to find minimum spanning tree for a given graph. So there are two very popular algorithms. One is Kruskal's algorithm and the other is Prim's algorithm. So we will begin the next session with Kruskal's algorithm and see how we can generate a minimum spanning tree for a given graph. So the summary of this session is that spanning tree is a subset of a connected graph. When I say subset, it's a subset of the edges, not the vertices. So all the vertices have to be included in the spanning tree with the subset of the edges, such that all the vertices are connected with the least possible number of edges. And a graph can have more than one spanning tree. And we've also looked at some of the general properties, and all the general properties that trees possess are applicable to spanning trees as well. And there are certain mathematical properties, particularly the number of spanning trees for a complete graph is n raised to the power of n minus 2. The number of edges that a spanning tree consists of is n minus 1 for a given graph with n vertices, and other mathematical properties we've seen. A spanning tree with the least cost is called a minimum spanning tree. So spanning trees are used in civil network planning, computer network routing, clustering, pattern recognition, and certain other areas as well. And this particular session has a quiz hosted on Google platform. So you are encouraged to open this particular quiz and then answer your questions, and your feedback will be given to you immediately. And all the questions you can make suitable assumptions wherever applicable, and all the questions assume that the graphs are undirected unless explicitly specified that it is a directed graph. If you have more than one option, choose all the options that are applicable. If it is a multiple choice question, choose the one that is the most appropriate one. So this concludes the session, and the notes are also uploaded. The lecture notes is also uploaded in the Google Drive, and the link will be shared to you. Thank you.